A fixed-wing drone equipped with 5 cameras was utilized to create a high-fidelity 3-dimensional model of the entire city, using the oblique photography technology. The 3-dimensional model contains more than 200 million polygons. In this analysis, the nonlinear time history analysis of buildings on a regional scale considering site-city interaction effects is implemented. Specifically, the buildings are simulated using the nonlinear multiple degree of freedom models, and the site is simulated using the 3D spectral elements. The ground motions of Wenchuan Earthquake are simulated using the Tsinghua supercomputer. Subsequently, the ground motions are adopted to simulate the interactive seismic responses of both the buildings and the site of the entire new Beichuan City. The influence of the complex terrain can be considered in this study, so as to produce a more reasonable analysis result. For example, the seismic accelerations at the top of the mountain is evidently different from those at the bottom of the mountain. By combining the regional seismic damage simulation of buildings and the detailed 3D urban polygonal modeling, the nonlinear seismic responses at any time are visualized in high fidelity for every building and every story. By combining the building models from oblique photography with nonlinear time history analysis results, the seismic responses of buildings are visualized in high fidelity. For special buildings, we can further establish their refined finite element models according to the design drawings, so that the seismic responses of every component of the buildings can be obtained. Then the simulation results can be combined with the building models obtained by oblique photography as well. Typical tall buildings at Beichuan City are shown as an example. Ground motions recorded in the region of 6, 7 and 8.5 degrees of seismic intensity according to Chinese code are inputted respectively. In order to display the response more clearly, the building deformation in the video has been amplified. Firstly, the record of Zhujiang Station in 2017 Zhujiang earthquake is inputted. The station is located in the region of 6 degrees of seismic intensity. Secondly, the record of Baoxingdi Station in 2013 Lushan earthquake is inputted. The station is located in the region of 7 degrees of seismic intensity. Larger response occurs in these buildings under Lushan earthquake than that in Zhujiang earthquake. For tall buildings, higher order vibration modes play an important role on the seismic response in addition to the first vibration mode, such that a significant higher mode deformation can be observed in the video. Finally, the ground motion at Beichuan City in 2008 Wenchuan earthquake simulated by Institute of Geophysics, China Earthquake Administration is inputted. The degree of seismic intensity is 8.5 approximately. The simulated ground motion has a long duration of 210 seconds in order to reflect the response completely. Significant higher order modal deformation can be observed at the early stage. By contrast, the deformation caused by the first mode dominates the last minute of response. The response under this simulated earthquake is larger than both Zhujiang earthquake and Lushan earthquake. According to the Chinese code, service level earthquake is defined as the earthquake with an exceedance probability of 63.5% in 50 years, and the probability is 10% and 2 to 3% for design basis earthquake and maximum considered earthquake, respectively. The intensity of design basis earthquake is also known as the seismic design intensity, defined as the seismic intensity with an exceedance probability of 10% in 50 years, which is associated with a peak ground acceleration. For example, design basis earthquake in a region of 8 degrees seismic design intensity has a corresponding PGA of 0.2 G. Cool text behind the video. One of the key challenges for seismic damage simulation is to obtain a reasonable ground motion input. The seismic wave propagation from the fault to the site is a complex process. Limited by computer capabilities, previous studies generally can only simulate low-frequency seismic waves. In this study, we cooperated with a team of Professor Hao Han-Fu from the National Supercomputing Center in Wuxi, which has the fastest in the world, Tsinghua supercomputer. Powered with the Sunway Taihu Light supercomputer, the full-band strong motion simulation of the 2008 Wenchuan Earthquake at the new Beichuan City was performed. Complex terrain and dense buildings may have a significant impact on the surface ground motion. As a result, the interaction between the site and the buildings should be properly considered. The buildings can be simulated using both the nonlinear multiple degree of freedom models and the refined finite element models. We further cooperated with the team of Professor Gang Wang from the Hong Kong University of Science and Technology to develop a computer program. Using such a program, the soil model of several square kilometers and hundreds of buildings are put together, and the seismic responses are calculated considering the site-city interaction effects. Another key issue in the study is to obtain the high-fidelity facade images and design data of the buildings. With the support of the Earthquake Disaster Mitigation Bureau of Beichuan County, we investigated the relevant design drawings of buildings. Moreover, in cooperation with Professor Xinzheng from the Institute of Geophysics, China Earthquake Administration, a vertical takeoff and landing fixed-wing unmanned aerial vehicle developed by China was launched, and more than 14,000 images were captured. Subsequently, the 3D building models with more than 200 million polygons were generated using high-performance computer clusters. The resolution of the 3D models is 0.035 meters.